Hello, and welcome to Settle the Stars. Episode 11, Jupiter, King of the Planets. Hey folks, this is Alexander Winn. Today, we'll be visiting Jupiter, one of the most historically significant, enigmatic, and downright dangerous locations in the solar system. As you probably already know, Jupiter belongs to a class of planets called the gas giants, which share unique characteristics that complicate visitation by humans. Currently, the technology simply doesn't exist to keep humans safe while visiting the planet, but with the aid of thousands of years of human observation from afar and remotely, we can do our best to imagine the conditions we might experience if we were to explore the planet in person. Before taking our imaginary dive into the clouds and storms of Jupiter, we'll illustrate the planet and its characteristics from the perspective of the scientific observers, satellites, and probes that contribute to our modern understanding of the giant planet. That being said, you may notice that conspicuously absent from today's discussion is an in-depth look at the staggeringly diverse array of moons around Jupiter. We'll be devoting an entire episode to those later. Jupiter is the largest planet in the solar system, but saying that doesn't quite convey the, gravity of the fact. Jupiter is huge. If you combined the mass of all the other planets in the solar system and then doubled it, you still wouldn't come close to the mass of Jupiter. It is so massive that rather than directly orbiting the Sun, both objects actually orbit around a shared gravitational fulcrum just outside the surface of the Sun. Much like your body would lean back as you swing a heavy bag of water around you, the Sun leans back to accommodate the large mass of Jupiter. By measuring that lean, astronomers could actually approximate the mass of Jupiter without even having to visit the planet. But that hasn't stopped us from constantly striving for a closer look anyway. To the unaided eye, Jupiter appears in the Earth's sky as a bright star, not quite as bright as Venus, but still easily viewable. Of course, as a planet, it follows a regular path across the sky against the backdrop of stationary stars, which make it an object of interest and importance for early observations. Of course, as a planet, it follows a regular path across the sky against the backdrop of stationary stars, which made it an object of interest and importance for many early observers. Among the earliest recorded observations of the planet are those of the ancient Babylonians, dating back to the 7th or 8th century BC, and a recent analysis published in 2016 claims that detailed calculations of Jupiter's velocity were conducted in Babylon around 50 BC. The Babylonians recorded the nearly 12-year cycle of Jupiter across the sky and used it as the foundation of their zodiac calendar, associating the planet with the Mesopotamian god Marduk, patron god of Babylon. It is thought that the ancient Chinese also used Jupiter's 12-year cycle as the basis for their own zodiac, surviving in the observance of the 12 animal years. Elsewhere in Asia, Hindu astrologers revered the planet by naming it Brihaspati, the teacher of the gods. They would refer to it as the Guru, which appropriately translates literally as heavy one. The name Jupiter used today comes from the Romans, who associated the planet with the chief god of the Roman pantheon, and translates as sky father god. Jupiter corresponds to the ancient Greek god Zeus. The name literally is a transformation of Zeus Pater, or Father Zeus. But the Greeks knew the planet as Phaethon, which translates to shining one or blazing star. So we can see that many ancient cultures observed and tracked the planet's movements, but it wasn't until the advent of optic technologies like lenses and mirrors gave rise to telescopes that astronomers really got a good look at the unique features of the planet. The biggest name discussed today in relation to Jupiter's early scientific observations is easily Galileo Galilei. Galileo was born in 1564 in Pisa, Italy, and is often praised as the father of modern science and the scientific method. He meticulously studied physics under the patronage of wealthy and powerful Italian rulers, and his defense of the theory of heliocentrism, that objects in the solar system orbit the sun as opposed to the Earth, famously ran him afoul of the Catholic Church, earning him much ridicule and even legal prosecution until his death under house arrest in 1642. But during his life, he vastly advanced the understanding of speed, velocity, and inertia, all foundational principles in our understanding of the physical world and astronomy. While commonly credited as the inventor of the telescope, Galileo actually based his designs on a hazy description of the same device that Dutch astronomer Hans Lippershey attempted to patent in 1605, without ever having even seen one in person. These first telescopes were simple cylinders with a convex lens on one end and a concave eyepiece on the other, and could manage a magnification of about 20 times. Galileo's early telescopes were intended for terrestrial use, to observe weather or distant armies on land or sea, but someone as curious as Galileo was bound to point it toward the sky eventually. And a good thing he did. Galileo is credited as the first person to describe the topography of the moon, which until then had been believed to be a perfect sphere, as well as the rings of Saturn, sunspots, and in 1610 he first viewed the 4 largest of Jupiter's moons, which still bear his name today as the Galilean moons. It was the observation of these moons and their regular cycles around Jupiter that solidified Galileo's conviction in Copernican heliocentrism, which directly contradicted the prevailing belief that all heavenly bodies circled the Earth. He was eventually forced to recant his conclusions and lived the rest of his life a prisoner of the Catholic Church in his own home. Jupiter's larger moons were easy to spot, but eventually telescopes became advanced enough to observe even more detail of the planet. In the 1660s, fellow Italian Giovanni Cassini described spots and colorful bands in the planet, with enough detail to be able to estimate how quickly the planet was rotating. English astronomer Robert Hooke was in competition with Cassini over who may have been the first to see Jupiter's famous Great Red Spot, but the earliest known drawing is attributed to the German astronomer and pharmacist Heinrich Schwab in 1831. Thanks to the careful notes of many of these early observers between the 18th and 20th centuries, we have seen that the Great Red Spot has undergone periods of growth and fading over the years. But it wouldn't be until the advent of spaceflight that humans would get their first up-close view of the atmosphere. In 1973, the first flyby of Jupiter was completed by the Pioneer 10 probe. Along with Pioneer 11, which passed Jupiter in 1974, they were not equipped with photographic cameras, but contained a collection of sensors and detectors for magnetism and radiation. The data they provided helped confirm many unobservable details, from the size of the magnetosphere around the planet, interaction of the planet with the solar wind, and chemical composition of the atmosphere. Anticipating the potential hazards for a spacecraft in crossing the asteroid belt, they were outfitted with 12 special meteoroid detector panels which could report on any small impacts encountered along the journey. The Pioneer probes were actually conceived as test flights for later launches that would take advantage of a rare alignment of the planets to visit Jupiter and Saturn, which would eventually be known as the Voyager missions. Voyager 1 and Voyager 2 both reached Jupiter in 1979 and provided most of the rich color images that many of us are familiar with from our childhood textbooks. In addition to the photographic cameras used to generate these images, the Voyagers were also equipped with their own arrays of sensitive magnetometers, spectrometers, and detectors to collect similar readings to the Pioneers. Building on experience from these earlier missions, scientists were also able to utilize the probe's telecommunications radio to measure physical characteristics of the planets and their moons, like density, gravitation, mass, and atmospheric composition. Not all of the equipment on the Pioneer and Voyager probes was scientific, however. Each of the 4 spacecraft also carried a cultural message. The Pioneer spacecraft each carry a special plaque designed by Carl Sagan and Frank Drake and illustrated by Carl Sagan's wife, Linda Salzman Sagan. Etched in gold anodized aluminum, the plaque is designed to visually demonstrate humanity's current understanding of science and convey some information about who we are. It includes a representation of the hyperfine transition of hydrogen, a universal constant measurement of length and time, and establishes it as a basis for other measurements throughout the drawing. Prominent in the image is a drawing of a man and woman whose height is provided in units of the hydrogen transition frequency, as well as a radial burst pattern of 15 lines with their own distances recorded in the same units. These 15 lines show the distances of various pulsars from the Sun and their orientation in relation to the Sun, as well as the frequency period of their pulses for identification, allowing an advanced civilization to pinpoint the exact source of the message, the location of Earth. Finally, each includes a map depicting the path of the probes through the solar system and out into wider space, and a silhouette of the spacecraft itself. Encoded within these measurements are depictions of various other measurements and characteristics intended to both demonstrate humanity's understanding of the physical world, as well as share information about ourselves and where we're from. It was a hugely important message that we sent out into the stars, but the scientists behind the Voyager missions decided to provide even more information. Affixed to the side of both Voyager probes is a copy of a gold-plated audio-visual disc known as the Golden Record, just in case some alien civilization should ever intercept them. These discs are a sort of time capsule of human civilization and life on Earth, including music compositions, whale songs, and a baby crying, as well as greetings in more than 50 languages. Each disc also contains an etching of some of the pictographs from the Pioneer plaques, in addition to special instructions for how to read the content of the discs. All of these efforts are an interesting glimpse into a difficult question to answer. What is the most important information we could send to other advanced civilizations? And how can it be conveyed in a way that can be universally understood? It's a question that didn't have to be considered too seriously, but as these 4 spacecraft were the first ever that would exit our solar system, their status as potential interstellar messengers bearing a permanent record of humanity continues to draw interest and spark the imagination. But before we get ahead of ourselves, let's get back to Jupiter. There's still plenty of exploration to do there. Never content with a simple flyby mission, scientists conducted an extensive orbital mission for long-term observation in 1995 with the Galileo spacecraft to study Jupiter and its moons. Galileo was a special achievement of its time, utilizing a new design that featured a fixed portion for radiometric and spectrophotometric readings, with a special spinning module to stabilize the craft and collect measurements from all directions. The Galileo satellite also included an entry probe, which would offer the first ever measurements from inside the atmosphere, including temperature, composition, cloud composition, and radio signals. The insights gained from the Galileo satellite were tremendous. In addition to confirming Jupiter's 90% hydrogen composition, wind speeds of over 400 miles an hour and temperatures reaching 570 degrees Fahrenheit before the entry probes were vaporized, the spacecraft also enjoyed a once-in-a-lifetime show, the massive impact of Comet Shoemaker-Levy 9. The comet had already been torn to pieces by tidal forces from a previous close call with Jupiter, so a bombardment of 21 impacts were observed as the fragments each collided with the planet. The largest of these is estimated to have released the equivalent of 6 million megatons of TNT, more than 600 times the power of the entire world's nuclear arsenals combined. The result was a fireball visible from telescopes here on Earth, and a gaping dark spot in the cloud layer over 7,500 miles across. The Galileo mission was definitely a big technological leap from the real Galileo's quaint little telescope less than 400 years prior, but one I like to think he would be proud to have bearing his name. Following the Galileo mission is the ongoing Juno mission, which arrived at Jupiter in 2016 and continues valuable data collection even now, well past the budgeted mission end in 2018. The spacecraft managed to capture the first images of Jupiter's North Pole in 2016, and will manage a few more flybys of the planet and several of its moons before entering a controlled descent into the atmosphere in 2025. And in case you don't think scientists have a sense of humor, Jupiter's moons are all named for Jupiter's many lovers in Roman mythology, and the Juno mission, to study those moons, was named after Jupiter's unhappy wife. Now, the amount of data provided by these flybys and orbital missions is incredible, and will take years to completely analyze. But what kind of picture do they paint of Jupiter? What do the mountains of data show? What we've learned is that Jupiter is very likely much older than the other planets in our solar system. Current models suggest that in the early solar system, when the sun was young, a solid core of water and other volatiles would have formed first, accumulating a gaseous atmosphere from the solar nebula before it dispersed. Jupiter is mostly composed of hydrogen, so it's a lot less dense than the rocky planets. To illustrate this fact, we can observe that while Jupiter's mass is equal to about 318 Earths, its volume, the amount of space it takes up, is equal to more than 1,300 Earths. Interestingly, it's believed that Jupiter is about as large as a planet of its mass and age could possibly be. If it had any more mass, the volume would actually shrink and become more dense due to the added gravity. Gas giants like Jupiter are usually composed of hydrogen and helium, with an outer cloud layer made up of molecular hydrogen gas that gradually transitions to a liquid or supercritical fluid gas-liquid hybrid as pressure builds deeper beneath the clouds. It's believed that many gas giants contain a small, solid core at the center of the planet, but from the Juno mission in 2016, scientists observed that Jupiter's core is more dispersed, possibly as the result of a massive planet-sized impact early after formation. The stunning photographs provided by these spacecraft visits have revealed a fascinatingly dynamic atmosphere. Because Jupiter boasts the deepest atmosphere in the solar system, it would be easy, and incorrect, to imagine that Jupiter is mostly made of wispy clouds. In fact, the atmosphere doesn't actually account for that much of the total radius. Of a mean planetary radius over 43,000 miles, the atmosphere only accounts for the first 3,000 miles or so, about 7% of the total radius. Still very impressive as atmospheres go, but not exactly a big ball of air. That thick atmosphere is divided into colorful bands we can easily see in photographs. The lighter areas are called zones, and the darker bands are called belts, and they're fast-moving currents moving in opposite directions from each other. The color and intensity of these zones can vary over time, but most are stable enough that scientists have named them. The varying colors are caused by compounds called chromophores, probably consisting of phosphorus, sulfur, or hydrocarbons being stirred up from deeper in the atmosphere and changing colors as they interact with sunlight. Wind speeds can reach over 220 miles per hour in the streams, where the bands meet intense turbulence and storms can occur. The most notable of these storms is, of course, the Great Red Spot, possibly observed as early as the 1660s by Hooke or Cassini, as we discussed earlier, but definitely described in 1831 and closely tracked ever since. It has been shrinking over the last century, with small pieces observed in 2019 actually fracturing off into smaller storms that dissipate over time. Currently, the storm is still quite formidable, especially by Earth standards. It towers over 5 miles taller than the surrounding clouds and stretches over 10,000 miles wide, or just a bit larger than the Earth. Similar to hurricanes on Earth, the center of the storm is relatively stagnant, while the edges of the storm blast at a staggering 268 miles an hour. With no solid objects to break the storm's momentum, it has continued to churn for centuries. But some scientists believe it may dissipate within the next 20 years. The Galileo mission provided evidence for lightning within Jupiter's stormy clouds, which hint at the presence of water clouds, perhaps below the outer layer of ammonia. These lightning blasts are a sight to behold, hundreds of times more powerful than any lightning on Earth, and capable of producing dazzling shows high into the upper atmosphere. And speaking of light shows, the north and south poles of Jupiter provide year-round entertainment. Here, the powerful magnetosphere guides particles from the charged solar wind into dazzling interaction with the upper atmosphere, causing a brilliant aurora like we sometimes see on Earth. If we dive deeper into the atmosphere, Jupiter becomes less familiar and more difficult to imagine for humans accustomed to life on Earth. By about 700 miles below the surface of the clouds, you would notice funny things happening to the hydrogen surrounding you. Here, the pressure and heat begin to build to such levels that the hydrogen behaves more and more like a liquid the further down you go. There is no distinct boundary between states, but before long you would find yourself submerged in a transparent atmosphere of liquid hydrogen. As you dive deeper, between 10,000 and 15,000 miles below the clouds, the hydrogen molecular fluid begins to form metallic fluid. I would generally advise against opening the window of any vehicle which might survive such conditions. But if you're strapped for cash, it might be worth a try to strike it rich here. It's been theorized that rainfall could be a regular occurrence, but instead of water, it would shower diamonds. Any conventional material protecting you would have vaporized long ago, but if you somehow had a working thermometer, it would read almost 9,000 degrees Fahrenheit. If that sounds hot, just wait. As you approach the diffuse core, temperatures rise to over 35,000 degrees Fahrenheit, with an estimated pressure of 4,500 gigapascals, over 44 million times more air pressure than we experience here on the surface of the Earth. If ears could exist down there, ours would definitely be popping. This core is the source of some of the most awe-inspiring power in the solar system. Electric currents within generate the magnetosphere that causes the dazzling polar aurora, the most extensive magnetic field we've encountered so far outside the sun itself. The field reaches all the way to Saturn, swallowing all of Jupiter's moons and capturing and accelerating solar particles into bands of dangerously powerful radiation. These radiation bands are extremely hazardous for both manned and unmanned spacecraft. Much of the data and images collected by the visiting missions have been corrupted by their surprising strength. Human travelers would need to be incredibly well protected to venture anywhere near Jupiter or its moons, as the radiation fields enveloping them can be several thousand times more powerful than the belts surrounding Earth. When it comes to spaceflight, there are plenty of reasons to be cautious. We have it pretty good here on Earth, and anywhere else we go will generally be pretty dangerous to visit. But Jupiter is in a class of its own. In 2022 and 2024, Europe and NASA will each launch missions to visit some of Jupiter's moons, with more missions from NASA and China in the planning stages for possible launch later in the decade. It may be generations before the technology exists to sufficiently protect human visitors, but in the meantime, we'll continue to send robots to quench our thirst for exploration. I hope you've enjoyed this exploration of Jupiter and hearing about some of the scientific leaps that have made our current understanding possible. We're not done with Jupiter yet, though. In our next episode, we'll be taking a closer look at the diverse and fascinating network of moons and other satellites in orbit around this giant, and the interesting implications for human exploration and the continuing search for life outside of Earth. In the meantime, be sure to subscribe if you haven't already. Settle the Stars is available on pretty much every podcasting platform, and we're also mirroring our episodes on YouTube at youtube.com/edgeworksentertainment. And be sure to ring that bell so you know when there's a new episode. We also have a Patreon page at patreon.com/edgeworksentertainment, where you can get early episodes and tons of other great rewards. The support of listeners like you is what makes this show possible, and I am so grateful to the people who have already joined. Thank you all for listening, and as always, happy terraforming. Settle the Stars is a proud member of the Edgeworks Nebula, a collection of intriguing and informative podcasts from Edgeworks Entertainment.
Edgeworks Nebula.